Hi. Okay, so last time we did Chapter 5, Section 6. We did the first half. This time we're going to go back and do a couple more problems that illustrate the definition that we're looking at here on the screen. Okay, so let's see. The definition says that L1 is polytime reducible to L naught, and the symbol goes like so. L1 is polytime reducible to L naught if there's a reduction function or transformation function f that's polytime computable, and so that sigma is in L1 if and only if f of sigma is in L naught. And I've tried to sort of make the point that it's called a transformation function because, in some sense, it turns problems in the language of L1 into problems in the language of L naught. So it gives us a way to think of L1 as being a case of, or maybe a special case of, L naught. And the example that we saw last time was that satisfiability can be thought of as a kind of clique problem. We translated it into a combinatorial problem down on the bottom of the slide. We translated it into a combinatorial problem, and then we saw that that's a that's a clique problem. We can think of it as a clique problem, and so F rephrased the problem in that way. We came up with a function that turned an expression into a graph, and the expression is satisfiable if and only if the graph has a clique of the appropriate size, namely the number of clauses in the expression. Okay, here it's a 3 clique. Okay, well, we want to do 2 more. So the first one is graph colorability, polytime reduces to satisfiability. Just to remember, a graph is k-colorable if you can split the vertices into k many classes. So a graph is called k-colorable if you can split the vertices into k many classes. They're traditionally called colors, so that 2 vertices have the same color only when there's no edge between them. So here, for example, you have a light blue and a light brown. Here is a dark brown and a light blue. Here is a light blue and a light brown and a dark brown. Never do 2 same colored vertices connect. So we have 3 groups of vertices. Light blue, there's a light blue, there's a light blue, there's a light blue, there's a light blue. So the first group of vertices, called light blue, are those 4. The second group of vertices, light brown, 1, 2, 3. The third group of vertices, 1, 2, 3, dark brown. Okay, and lots of problems are expressible as color problems, so that when you first see it, you think it seems a little like toy, but it's not. It turns out that a lot of problems are expressible using colors. So this is a 3 coloring of this graph. Okay, and we're going to illustrate that a graph k colorability reduces to satisfiability. Graph k colorability less than or equal to sub p satisfiability. By focusing on the k equals 3 construction, the larger k's work the same way. Just as a comment, the k equals 2 case is somewhat different. Just as a warning that there's something different about 2. The k equals 4, k equals 5, k equals 6 all pretty much work the same way. You'll see what happens when it happens. Okay, so what we have to do then, if you follow the definition, last time we went on at some length about what f is doing, but here we're trying to return a little bit back to the sort of formal mathematical definition. So if you follow the definition, it says we have to show that given an instance of graph colorability, we can translate it into an instance of satisfiability. And that translation has to take polytime. Okay, so we're going to take in a graph colorability problem. We're going to put out a satisfiability problem. Okay, so we'll denote the set of, we need 2 languages. We'll denote the set of 3 colorable graphs as L1 and the set of satisfiable propositional logic statements as L0. So now we've described them both as language decision problems. We want to show that L1 less than or equal to sub p. The L1 polytime reduces to L0. So we got to produce a translation function f. It inputs a graph G, because that's what is in L1, and it outputs an expression E, because that's what's in L0. And it has to be the case that the graph is three-colorable if and only if the expression is satisfiable. Okay, so this is what we're required to do. At some point, you have to think out what's the answer. So that point comes now. So the function is going to build the expression by including clauses that describe, in the language of propositional logic, the constraint that the graph has to meet. So here's what's going to happen. If we have a graph with n many vertices, then the expression will have 3n many Boolean variables. There'll be Boolean variables that I'm going to name with the letter A, n of them. There'll be Boolean variables that I'm going to name with the letter B, n of them. And there are Boolean variables that I'm naming with the letter C, n of them. Well, I often call Boolean variables P, Q, R, but here I need more than 3. The idea of those Boolean variables is, suppose that the vertex I gets the first color. Then we're going to have that AI equals T, and the other two are F. If vertex I gets the second color, then BI equals T, and the other two are F. And if vertex I gets the third color, then CI is T, and the other two are F. So you see, I'm starting to build up an expression. It's going to have a lot of propositional logic variables. I'm starting to build up an expression and thinking about it will be satisfiable if and only if sort of thing. So for vertex VI, I have to express that the vertex gets at least one color. So I need AI or BI or CI. So either AI is true or BI is true or CI is true. And that tallies with what's in the prior paragraph. And now I got to express somehow the constraint that you cannot have same colored vertices sharing an edge. So for each edge, VI, VJ, I'm going to include 3 different clauses. Not AI or not AJ, not BI or not BJ, and not CI or not CJ. So just to focus on the third, it cannot be the case that both vertex I and vertex J are the color C, or the third color. Likewise, it cannot be the case that both vertex I and vertex J are the first color. It cannot be the case that both vertex I and vertex J are the second color. Okay, so that's how I express that you cannot connect 2 same colored vertices. And then I'm going to make the Boolean expression E is just going to be the conjunction of all those clauses. So here is an example. Simple example, I think, gives the idea much more than any amount of description. So I have a simple graph, 1, 2, 3, 4 vertices. The first line up here says vertex 0 gets a color, vertex 0, 1 gets a color, vertex 2 gets a color, vertex 3 gets a color. The next line says that you see this edge here between vertex 0 and vertex 1? It says that however you assign the colors, it cannot be the case that vertex 0 and vertex 1 are share a color. It must either be the case that vertex 0 is not color 0, or vertex 1 is not color 0, or maybe both. Both would be okay. It cannot be the case that it either has to be the case that vertex 0 is not the second color, or vertex 1 is not the second color, or vertex 0 is not the third color, or vertex 1 is not the third color. So I've managed to express that it's not the case here that both vertex 0 and vertex 1 share color 0, or color 1, or color 2. They can't be the same color. And you just reiterate that for all the edges. This edge here, this edge here, this edge here. So what I have here is a somewhat complicated, because propositional logic is kind of an oddball programming language, but a somewhat complicated statement that says everybody gets a color and never do connected vertices get the same color. So I constructed the expression in such a way that there's an assignment of truth values for the variables if and only if the graph has a 3 coloring. And all I got to do then to finish is check that the translation function is polytime. Technically, the translation function doesn't take in graphs. Technically, it takes in bit string representations of graphs, but come on. And technically, it doesn't output expressions. It outputs a bit string representation of the expression. But come on, can you convert from here, from the left-hand side to the right-hand side in polytime? I think so. I'm not going. Can you convert from a bit string representation on the left side to a bit string representation? I'm not going to go through the details. Okay, one more problem to go through to illustrate the definition. Deliberately chose one where I think the problems might be a little less familiar. So first problem is vertex cover, second problem is set cover. Vertex cover inputs a graph and a number b. It asks if there are vertices so that each edge contains at least one such vertex. So if you looked at this graph here, for example, the graph I've expressed it as some kind of distantly applicable problem, but really I'm looking at the graph and I'm saying, can you get away with four vertices in such a way? Can you get away with four vertices in such a way that you have covered every edge? So what do you do again here? So I'm going to take that vertex, that's one. And if I take vertex v1, I don't get this edge. So I guess I'm going to take v5, okay? And then v7 gets me an awful lot of edges, so that's a good one to pick. And I think v2. I think now that with the choice of those four vertices, I think that I've got a vertex on every edge. I've managed to snag a vertex on every edge. And the way the problem is stated, you have to put a guard so the guard is watching each corridor. So with a guard in those four places, I'm watching each corridor, each edge. Okay, so vertex cover, and then the second is set cover. Set cover inputs a set U and a number b and a collection of subsets of U. It asks if there's a subcollection whose union is the entire set. So can you find b many of these capital S's where you union them together to get the entire set? So some similarity between the two problems, and again that reinforces our idea that we're going to translate instances of vertex cover to see how they can be viewed as set cover problems. And the problem, the example that I have here is you're hiring people and you have 10 skills to cover, skill 0, skill 1, up to skill 9, and the 4 applicants check off. So the first applicant says, I can cover, I have skill 1 and skill 4. The second applicant says, I have skill 2, skill 3, skill 4, skill 5. So can you get away with hiring here only 3 applicants? And I think the answer is yes, because if you take S1, S2, and S3 and union them together, you in fact cover every single one of the skills. So this S0 person happens not to be needed. So the two problems, at least on the face of them, I think are less familiar than the ones in the previous slide. So trying to illustrate how a typical sort of presentation will go. And also the two problems seem somewhat alike. You're trying to pick in such a way kind of thing. So we're going to, how do you go through these if you're presented with such a problem, for example, how do you go through it? So we're going to show that vertex cover polytime reduces to set cover by showing how to translate instances of vertex cover, sorry, I'm supposed to be underlining, instances of vertex cover into instances of set cover. So I'm going to write down what does an instance of the one look like and what does an instance of the other look like. So in vertex cover here, instances look like G comma B. And we're imagining that some set of B many vertices covers all the edges. Instances of set cover up here look like this. U comma set of capital S's comma B, where some number of B many of the S's covers capital U. B many of the capital S's covers capital U. And of course, we have to produce a polytime computable function that takes in sigma and outputs f of sigma, and with the property that sigma is in L1 if and only if f of sigma is in L0. So we take in pairs G comma B, we output triples U comma the set S0 through Sm comma capital B, and we have to satisfy this constraint. And of course, it has to be the case that f is polytime, although that doesn't seem to give us too much trouble. Doesn't mean you can ignore it, but it means that often it just proves to be, you look at the example and you say, yeah, obviously you can do that in polytime. Okay, so what do we do? In a typical presentation of one of these, what's the presentation going to say? Okay, so we have to take in a pair, G comma B. We don't have any choice. That's the way the definition asks us to work. So I've got to decide what is the triple, U comma set of capital S's and B. So U is going to be all of G's edges. U will be all of G's edges. for each of G's vertices, Vi, you take capital S sub Vi to be all the edges where Vi lies on that edge. It's one of the two endpoints of the edge. And then you just define f of sigma to be the triple. And of course, f of sigma has to be a triple. So it's u comma s naught through sm comma capital B. So same B. The B up here is the same as the B down here. And so again, before you really had much chance to think about it, the definition requires us to take in things from L1 and to put out things from L0. So we are translating problems stated in the language of L1 into problems stated in the language of L0. Clearly, you can do F in polytime. Further, for the bound B, there's a collection of S's if and only if the collection of V's is a vertex cover of G. So that's right, you get every edge if and only if the vertices do indeed give you every edge. That's exactly what a vertex cover means. The vertices give you every edge. So the S's do indeed give you all of the edges if and only if the vertices lie, the vertices that you pick lie in total on all the edges. And the example here from the previous slide, but I'm not gonna zoom back and look at it again. So the corridor guards problem. So you have the corridor guards, the four that I circled. Capital U would be A, B, C, D, E, F, G, H, I. And, you have that the S sub V naught, there it is. Oh, S sub V1 is A, B, D. A, B, D, those three. S sub V2, if I can find it, B, C, E. All the way out, etc. And then the set cover S sub V1, S sub V2, S sub V5, S sub V7. Well, we know that S sub V1 takes care of A, B, D. We know that S sub V2 takes care of B, C, E. We know that S sub V5 takes care of D and G. I know D is a repeat, but there's no harm in it. And we know that S sub V7 takes care of F, H, and I. So there's a set cover if and only if there's a vertex cover. And again, it's pretty clear here that F can be done in polytime. Okay, so these reductions can be tricky. They give a person trouble. They're always boiled down to, at some point you have to be clever. Of course, at some point you have to think what to do. At some point, there it is. At some point you have to think what to do. That's, of course, that's right. At some point you have to solve the problem. But it does help to remind yourself what it is that you're asked to do. One of the tricks I find to solving these, helps a person organize their thoughts, is to say, well, what does F have to input and what does F have to output? F doesn't input the problem vertex cover. F inputs instances of vertex cover. F doesn't output the problem set cover. F outputs instances of set cover. So you are translating instances of L1 into instances of L0. In this case, you're translating pairs into triples. And of course, in such a way, at some point you have to solve the problem. But it helps to understand what problem it is you're trying to solve before you find yourself, sunk. Okay, all right, very good. Very good. So see you next time.